Thanks, Michelle, and I'll reiterate the gratefulness to be involved in this project. I'll basically be giving an overview of the downscaling component, task 3 of the overall project. So basically it's the background to the results that were used in the presentations that Graham and Mark gave yesterday, and also basically summarising the large technical report that's available that the people have referred to. So myself and my colleague Gavin Fu are the authors of the technical report, but I have to acknowledge that a much larger team was involved in this work across all the participants of the project and wider, so I acknowledge everyone who's been involved. So I'll go through some background to some extent on projections and uncertainty, and then go straight into the downscaling and showing results of the projections for the South Australia's natural resource management regions, and then some key findings and caveats and a summary. So I think you've heard it mentioned a few times, but it's very important to start with this declaration that projections are a plausible future, but they are not the actual future because of the uncertainties involved on how the actual climate will evolve over the next century. So a prediction is a specific statement about the future, and we're used to weather forecasts, which are very accurate these days, the most likely future, often based on model results. A projection, in comparison, is what could happen if certain assumed conditions prevail in the future. And they're used in scenario analysis. So a scenario being a series of events that could lead from the present to a plausible but not assumed future. And so that's just a schematic. There's no actual units on the time. It's just to show that as you go further out into the future, your ability to produce forecasts drops off at some stage, and then you're in the scenario space using projections because your uncertainties are increasing and what you can predict is decreasing. So just a bit of background there. Also a bit of background to the climate change modelling, and you've heard quite a bit about GCMs and climate modelling and how it's now done in the IPCC. But just to summarise, some of that material was presented yesterday, but we're now using in the climate projection space representative concentration pathways, which you can see there the different levels of CO2 in the atmosphere for a range of different RCPs, and they're actually compared to the old SRES scenarios that you would have used previously, such as A2 and B1 that you're familiar with. And that just summarises what those numbers mean. So by the end of the century, there'll be an extra 8.5 watts per metre squared radiative forcing in the RCP 8.5 scenario, likewise 4.5 for RCP 4.5. And so our downscaling has used a medium, sort of intermediate RCP 4.5, which is similar to the B1 used in the previous IPCC, and we've used RCP 8.5 as a high end. As was mentioned also yesterday, global emissions are tracking that high end, which was similar to A1FI, that a lot of you would be familiar from previous work. So how can downscaling add value to GCM output? Well, obviously of great importance is the second point, which refers to in a lot of the applications yesterday, the utility of having climate change data at the scale that can be used in natural resource and built environment modelling, such as the work that Graham showed. But also it can actually add information. It can actually pick up signals from the large scale synoptic changes that the GCMs and relate that to local scale, regional scale or point scale rainfall patterns that you just can't pick up from GCMs. An example would be, depending on if you've got rain stations on a valley, the aspect of the valley, so a north-facing versus south-facing or an east-facing, west-facing side of a valley might get quite different rainfall patterns for the same overall regional climate. And so the downscaling can pick up those different responses to the large-scale changes that the GCMs are projecting, but you could never get that from GCM scale results. And I'll be concentrating on statistical downscaling, but there's also a large body of research into dynamical downscaling, which was also mentioned yesterday, which is running climate models at finer grids to resolve some of those processes, but it still doesn't get down to the station scale that you often require for your impacts models. So I'm not going to go into any of the technical details of the statistical downscaling model we used. The background to that model and the references to papers are in the technical report for people who are interested in learning a bit more. But basically, it's a model developed over a number of years because it has been found to have application for hydrological applications, and particularly reproducing the statistics of at-state rainfall. Not just means and variances, but runs of dry and wet days are quite critical to semi-arid catchments that we have in southern Australia. So getting those runs of wet and dries is quite critical. So the model has a concept of the weather state, which is the patterns of rainfall over time. So it's a daily model, daily patterns of rainfall. And the model simulates those, after calibrating to a number of atmospheric predictors, it can simulate the sequences of transitions between the dominant rainfall patterns. So we can generate stochastically many realisations of the rainfall. And then we simulate non-rainfall variables, temperatures, solar radiation, vapour pressure deficit, and aerial PET, conditional on both those weather set sequences and the long-term trends generated by the GCMs. And again, a lot more technical detail in the report. This probably summarises this is a bit of a similar summary to one of the Mark's slides. Mark mentioned 200 stations. I'm quoting 180 here. That's because in one of our NRM regions, which is the Adelaide Mount Lofty ranges, the Onkaparinga study catchment was part of that, so there was a bit of doubling up there. Maybe he counted some of those stations twice. So for each of 7 NRM regions, the reason I'm saying 7 here is because the most arid westerly AW region didn't have enough stations of high enough quality to be able to calibrate models to that region, so we've only got 1 station, as I'll show in a subsequent plot. So we're using 15 GCMs, all CMIP 5 GCMs, and we're simulating for a historical period, which is 62 to 2005, and the 2 future projection periods for those 2 RCPs. So that's from 2006 out to 2100. So being daily data, that is quite a lot of data. So 178 stations, 100 stochastic replicates, because for the same inputs to the downscaling model, we can run it in sort of Monte Carlo style to get lots of representations of potential future rainfall daily sequences, and then the other variables conditional on that. And as Mark mentioned yesterday, it's about 800 to 900,000 files, about 1 terabyte of data in total text files, 1 day per line, with those variables, as mentioned previously as well. So that's just a summary of the station network that we've used. And the station network was selected based on 2 main criteria. Relevance to hydrological research, so that was working with Task 4, and particularly Graham Greene, to select stations in areas of importance for South Australia's water resources issues, but also very important to assess the data quality, because so based on where you'd like to have results, you've got to assess all the stations in those regions, but some of those weren't of sufficient quality, so we had to cut down. So there are some areas that don't have as much density as other areas. And so the downscaling model was calibrated individually to the different NRM regions on a seasonal basis to give us an ability to relate synoptic climatology to local scale rainfall processes. And as you can see, there's only 1 station, as I mentioned, in the AW region. So that station was included in the Arid Lands NRM model. So I'll just show some examples of what's in the technical report, and to highlight and also sort of give some background information how to interpret the results in the report. So looking at the Adelaide Mount Lofty ranges modelling for that set of stations. So the 2 main ways we're showing the results in summary form in the report is through time series and bar plots of ranges. And I've just tried to align those to get the zeros lined up roughly. So these are percentage, and this example is for the Adelaide Mount Lofty range for the summer season, December, January, February, for RCP 4.5, just as an example. So it's the rainfall anomaly in percentage relative to a baseline period. So the time series plots in the report are showing the change relative to the full historical record period of the simulations, which is 62 to 2005, whereas the bar plots are relative to a 20-year period, 86 to 2005. And the reason for that is because we're showing results in 20-year blocks moving through the century. So we wanted to have the projections of those 20-year blocks relative to the same length period in present-day conditions. So the middle line is a 20-year moving average of the median. So half the downscaled results, so half the GCMs downscaled give results above that and half below that. Similarly, in the bar plots, half above and half below. We're showing two sorts of information. We're showing sort of 20-year moving average variability, so basically a measure of climatology, and we're also showing interannual variability. So the darker colour in the time series plots is the range of 20-year averages, and these are averaged across all stations in that region. Likewise, the solid bars are the range for the 20-year climatology, and the lighter range is for all the individual years in a simulation, and likewise the thin lines are all the years. So just going to some examples. So for the precipitation projections, showing 4 seasons. So top left is summer, then autumn, then winter, then spring. So this is for 4.5, these ones, and these ones down here was, summer's blocked out a bit, and this is for 8.5. So you can see that all the seasons are showing the median trends are decreasing. The median trend decreases for the higher forcing, the higher climate change signal is more. There are still periods, simulated periods from certain GCMs that have the 20-year mean above the current mean for certain periods in the future, with the exception of spring, where basically after about 2030 or so, all the 20-year periods are below the observed. But you can see there's obviously interannual variability, so you're still going to have some wet years in the future. For example, even for the 20-year period averaged over the last 20 years of the century, you can still have years where the rainfall is above the current long term. You can have individual years where rainfall is above the long-term mean. And so maybe the point to emphasise is the strengthening of that change with the higher concentration scenario, and the fact that the spring season is relatively more decreased than the other seasons, and the large range across the multimodal downscaled ensemble. Some of the ways we're comparing results in the report is to look at changes comparing the rainfall that you get directly from the GCM, so a very large grid square resolution, which you can't really use directly for impacts modelling, because the actual magnitudes are quite different to the observed rainfalls. But just to show the range of change comparing the scale of the GCM to the scale of the downscaled results. So for basically the 4 seasons, summer, autumn, winter, spring, each of the panels is a period in the future, so 2020 to 39, 2040 to 59, 60 to 79, and end of century 80 to 99. And there's sort of 3 key points from this sort of plot, because each plot is showing both of the RCPs, so that for each season the 2 left ones are for RCP 4.5 and the 2 right ones are for RCP 8.5, and they're showing the GCM as the first in each pair and the downscaled in the second in each pair. So the messages here are that in virtually all cases, the downscaling reduces the range because rainfall from GCMs is a lot more uncertain because of the inadequacies of GCM's representation of the rainfall process. And also, in a lot of cases, the actual median drying is stronger from downscaling than the GCMs. And also, it's very evident that as you progress towards the end of the century, the drying gets stronger, and also the relative difference between the 4.5 and 8.5 gets stronger. Another issue is how does GCM data quality affect the downscaled results? So taking the results that Chai showed earlier, where he's assessed GCMs based on their ENSO and IOD performance, of the 15 GCMs we were able to downscale from, Chai has assessed 12 of those, and 3 he was unable to because of lack of relevant data. So of those 12, 6 are classified in Chai's work as relatively poor compared to the overall models, and 6 are classified as relatively better performers. So we call them the 6 best and the 6 poor. So the pairs this is all downscaled results now. We're not looking at direct GCM results. So again, we're showing 4.5 and then 8.5 for each season. So the pairings now are the poorer GCM downscaled results are the left-hand one, and the better ones are the right-hand one. So you don't get decreased range necessarily in all cases for the better GCMs, but what you tend to get is less of a change. So basically, if you concentrate on 6 better GCMs, the actual median change in most cases is less, but not in all cases. The other variables, similarly, there are time series plots and bar plots of changes. I'll just show a few time series plots. So for maximum temperature, again, under the 2 scenarios, you can see the different seasons, the different ranges of change as you progress towards the end of the century. And you see very strongly that the higher emission scenario has a much larger change than the lower emission scenario, and the range increases as you go. So basically, the GCMs are diverging more in the high emission scenario than in the medium emission scenario. Likewise, for minimum temperature, all the seasons are increasing, but a large uncertainty, particularly in certain seasons relative to others, and a large increase for the high emission scenario. And the reason we concentrated on focusing on temperature, solar radiation, and vapour pressure deficit was because we need those as an input to the calculation of aerial potential evapotranspiration. And so in a drying climate, you're obviously going to have more water limiting issues, but also in a warming climate, you're going to have more PET. So that is shown here, how in all those seasons and relative to the strength of the climate change signal, how you get increased APET and, again, larger range from the strongest emission scenario. So some key findings. I've tried to summarise the type of results you can find in the report. So the 2 emission scenarios diverge as we move towards the end of the century when we downscale from the GCM's simulations of those results. And the level of uncertainty increases with the higher emission scenario and as we move through the century. And that's a consistent finding for all the NRMs. I only showed just a few highlights from the Adelaide Mount Lofty Ranges NRM results, but that's consistent across all the regions and all the weather variables. The range of downscaled change, particularly for precipitation, is consistently less than the range from the GCMs directly. So the downscaling has achieved one of its original aims, which was to narrow the uncertainty range in the projected series. When we look at assessing GCMs for their ability to reproduce the key drivers that are relative to important, as Chai went through in his research, we can classify, as I said, we classified 6 better and 6 poorer GCMs, and the magnitude and range of change from the better GCMs is less than for the poorer GCMs when we downscale from them in the majority of cases. So majority of NRM regions, seasons and variables. So that suggests that sound GCM selection also narrows the uncertainty range. Another finding is that the spring season is projected to experience larger relative decreases in precipitation and increases in temperature and APET compared to the other seasons. And the projected warming and hence the APET increases are larger as you move further inland and north, which I wasn't able to show in this short presentation because I only showed results from one region, but that's a consistent signal as well. Some of the caveats that are mentioned in the report and also worth emphasising. So the downscaling is totally reliant on the atmospheric predictors that we take from the GCMs to drive the downscaling models. And the quality of the GCM simulations in the future may contain unknown unknowns, to use a popular phrase. So there could be deficiencies in the GCMs that are unquantified, and so we're always going to be uncertain in when we try and assess the ability of the downscale projections to simulate the range that is relevant for the true future. As I mentioned at the beginning, I want to reiterate, the projections are not forecasts. And at any time in the future, the actual climate variability may either enhance or suppress the projected climate changes. So you could, in my time series plots, you could see that there was still a lot of variability, inter-annual and inter-decadal variability from those suite of GCMs. But you can't go and look at those time series plots and say, oh, the median is going up in this particular decade, because those are independent runs of the GCMs. They're not forced by real data at that time, obviously. So, for example, if the GCMs are saying a particular decade is dry relative to long-term climatology, if you just happen to have the natural variability working against that, you can obviously still have wetter conditions in those periods. Whilst the Goyder climate change projections are the most comprehensive and up-to-date available for South Australia, it's recommended that comparisons of other projection products should always be undertaken in any thorough investigation. And I know Mark and Graham have been involved with discussions with the broader CSIRO Bureau of Meteorology projections, and there is guidance material on the Goyder's website, or links to that as well. And also the Climate Change in Australia website has information on their range of downscale projects, which aren't as site-specific, but they're more at a regional scale. So in summary, climate change projections are uncertain. They're a tool for scenario planning. They're not telling you exactly what the future is going to be. They're telling you the most likely or plausible directions of change. And the results that we've seen today and in the report show that warming and drying is a consistent projection for South Australia. The downscaling provides site-specific time series. As we've seen in Graham's presentations, they were able to use them in a number of impacts modelling investigations. The results shown today and in the report show that both the downscaling and the selection of better quality GCMs in terms of the drivers of South Australia's rainfall narrows the range of uncertainty, which is a useful achievement of this project. And also, as Mark mentioned yesterday, there are guidance materials for using the downscale projections and assessing the resulting scenarios from the websites. So with that, thank you.